I may not accomplish everything I want to. We'll see. All right. So I'm going to start with the Ramsey theory on omega. Can somebody check that my mic is working for the online people?
Yeah,
is that good?
That's fine.
Right, so Ramsey theory on omega, we have the finite dimensional which is for all m and r, omega arrows, omega m r. All right, so I think by now in the semester, people are getting used to this notation, but I will just write this out for a quick second. So for every coloring, taking m size subsets of omega into r, there's going to exist an infinite set m such that chi on little m size subset of big M has only one color. All right. So now let's move to Ramsey subsets of omega. So a subset. Yeah. I mean, it's still true. But very boring. Okay. And so X subset of infinite subsets of omega is going to be called Ramsey if it behaves like a nice partition. So if whenever you have an M that is infinite, you can cut down to a smaller infinite subset such that below n, you're either in or out. Okay, so the script X is acting like a coloring of infinite subsets of omega into two colors, right? And you can either cut down to an infinite subset where you're color 1 or color 0. Okay. All right, so right, this would be omega arrows omega. Well, let me not write that. Okay, so now finite dimensional Ramsey theory. On infinite sets. Okay. The finite dimensional, but we're working on infinite sets. That is Ramsey's infinite Ramsey theorem, right? So would say that for every m and r, if I subset of omega to the m, then this set. Okay. It's Ramsey. All right, so I'm trying to translate from the way you normally think about the infinite Ramsey theorem into topology. Okay. What? Oh, yeah, R is 2 here. Yeah. Okay, so I've got basic open sets, finite heads into omega, but they all have no. This was M, that's correct. they all have the same size. Okay. So you can think of this as a very uniformly clopin coloring. Okay. So what's intermediate is Nash-Williams. Says that implies every clopin set is Ramsey. Okay, it's actually stronger than that. It's really stated in terms of partitions of sets of finite subsets of omega, which are unbounded in their size. And if you have a Nash-Williams family, which means that no member of your family end extends another member of your family, then if you partition it, you can cut down to an infinite set where you're in one piece of the partition. Okay, so it implies clopin sets are Ramsey. And then we have Galvin's theorem, which implies that open sets are Ramsey. And then we get to our Ellen-Tuck topology. So this is a topology which refines the metric topology. On the bare space. And has basic open sets of the form. Matthias forcing. Okay. Basic open sets of the form. Let's put that here, SA, where S is finite, A is infinite, okay. And SA is the set of X's, which are infinite, which end extend S and are contained in A. Okay. So this is a topology which refines the metric topology. And now with respect to that topology, we can talk about Ramsey-ness still. So one more definition. So a set X is now going to be called completely Ramsey. Which we'll CR if for every non-empty basic open set SA, there is some B in there such that SB is either contained in X or SB disjoint in X. Okay. So this has just taken the Ramsey property and now done it relative to any infinite set. Okay. Key important point here is that this S stays the same between A and B, right? We don't have to go further to get inside. All right, so Galvin Prickry now. Implies that Borel sets, Borel in metric topology, are completely Ramsey. Okay, and then Silver extended that to analytic. And of course, the next step would have been Suslin, but then Ellen-Tuck surpassed that quite quickly and characterized the completely Ramsey sets in terms of this topology. So a set X is completely Ramsey if and only if it has the property of bare with respect to the Allen-Tuck topology. Okay. So this is our progression from the infinite Ramsey theorem, which is really a finite dimensional theorem, but on an infinite set, to infinite dimensional Ramsey theory because we are coloring infinite objects. Okay. And why do we bother with topology at all? Because axiom of choice. Okay, I mean, there's things called, these nice partition cardinals and, models of AD and stuff, right? But once you have choice, you can make a partition which will not be Ramsey at all. So we have to use these topological or definability ideas to characterize them, and then Allen-Tuck completely did that. Yeah, that's a silent double F. There we go. Thank you. Okay. All right, so let's now get into, yes.
Historical remark that Bortowski's book shows up in the Olympics paper, and the authorist topology is all over the place there.
Yeah.
And he did not see it.
He didn't, and even Galvin Prickery used it too, but they didn't see it either. Yeah. Right. Yeah, it is to be right. That's true. That's true. Yeah. And you also call it exponential in your book too. Yeah.
Exponential topology.
Yeah. Yeah.
Yeah.
Yeah. Let me note that just for the folks who are not indoctrinated into this. All right, so structural Ramsey theory. So let me back up to finite structural Ramsey theory, because that's the whole subject of its own with a very long and beautiful history starting in the 70s, a little bit before. And there are a heck of a lot more results on finite structural Ramsey theory than there are on infinite. And it's still ongoing. Okay, so the finitary means all objects are finite. So class K of finite objects, structures, has the Ramsey property if. So for all A's which embed into B in K, and for every R, there exists an M and there exists a C, which should embed B such that C arrows super A sub R. There we go. Okay. So C took the place of M. And right, so these are all finite objects, but if you look at Frise limits, you can also state this in a way that's going to be indicative of the progression of the results. So equivalently, for K, and let's just assume this is a Frise class. Okay, so for K being the Freisey limit of script K. This is equivalent to saying K arrows B super A sub R. Okay. By compactness. All right, so let's look at some examples now. I have 5 examples to sort of hold on to for through the talk. Okay, earliest example, simplest example. Finite structures and their Freisey limit. Okay, so 1 is finite linear orders. Right, finite linear orders really are just Ramsey's theorem, right? Their Freisey limit is what you get when you construct the back and forth argument, putting them all together. So we actually end up with the rationals, not the natural numbers, right? So Q as a dense linear order without endpoints, right? So if you take, right, what is a copy of this or a substructure of this isomorphic to it? It's any subset of Q, which with this inherited order is again dense linear order, right? But it might have a lot of gaps with respect to the original. 2, finite ordered graphs. Right, so what is their F-lim? It's the Rado graph. These are finite structure, Freisey classes. With the Ramsey property. Okay. So the Rado graph is what you get by taking the Freisey limit of the unordered graphs.
Could I interrupt for a moment?
Yeah.
The camera is still focused on the first 2 blackboard. Now we're in the right place.
Thank you. Thank you, Doris. Okay, so why do we have, we didn't have to go to we can go to the ordered Rado graph too, but there's something sort of hidden right here that's also invisible, right? Which is the small Ramsey degrees. And if you take away the order from here, you don't get the actual Ramsey property, but you still get a bound on the number of colors that you can cut down to, right? So you could, I mean, the Freisey limit of this would be the Rado graph with an ordering on it that looks like the rationals. You can consider those. I'm just going to consider Rado graph today. Okay. Third, finite ordered K-partite graphs. Right, so these are actually now involving unary relations because you've got 1 unary per number in K to divide up the partitions. So this is K unaries and 1 binary relation, right? And then it gets to the generic K-partite graph. And fourth, finite ordered K-click free graphs. And those turn into Henson graphs. And fifth, we talk about finite linear orders with a convex equivalence relation. Meaning an equivalence relation whose equivalence classes are convex. When you take its Freisey limit, you end up with we're calling Q sub Q, which is basically Q's copies of Q, each of which are convex in themselves. Okay, so those are some examples of Price classes and their limits to hold on to. Yes.
Convex class.
Convex equivalence classes, yes, yeah. Yeah. And you can actually make a whole hierarchy of these things with nested equivalence classes, nested equivalence relations, each one superseding the previous one. Yes. No, what I'm saying is I want to concentrate on this one. On all of them, just drop the ordering. I mean, except for this one. Yeah. But you could consider also an ordered version of the radograph, and we have results for that too.
Okay.
Yeah.
His remark was, okay, because there are one side Price class, the other side limits. So there should be ordering. there.
Yeah, yeah.
Order,
Yeah, sure. Okay. But the point is that you need the order to have the Ramsey property on the Price class. But when you get up to big Ramsey degrees and infinite dimensional, you can drop it. Okay, so let's see. I want to get now to infinite dimensional structural Ramsey theory. And then we will backtrack to finite dimensional to show how it poses obstructions and what we do with those obstructions. I think they can see me. I think that was a while ago.
Yeah, okay, fine, yeah.
Yeah, that's right. I mean, you guys don't have to watch the screen. Okay, so let's jump to infinite dimensional and see what we would like, and then figure out what we actually can get. Okay, so K is a Price class, big K is its Price limits. Equate, or let's let the natural numbers be the universe of K. Right. So what we're trying to do is we're trying to extend some, whatever we can of these theorems to infinite structures, right? And so the first thing you have to do is, make it a subspace of the bare space, make it have a reasonable topology, right? And so if you think of just giving it the universe omega, already you'd have a subspace of the bare space on the subcopies of this. So we want to, okay, then the copies of K inside of K form a closed subspace of the bare space. And KPT said, we want a theorem of the form K arrows star K super K 2. 2005 paper, right? So we want a theorem of this form. Now star means subject to some definability criteria and possibly more, right? And we find out that we need the possibly more because of big Ramsey degrees, right? So obstacle. Is the big Ramsey degrees. I believe it's closed. I believe it's closed. Because once you start, you can always like, you have finite initial segments that are starting the right way.
You're thinking the Q inside the Q, can you make gaps in the limit? The gaps like 2 points that they have nothing in between.
Okay, if you have a fixed enumeration and you're doing let me modify this. So copies with respect to the omega enumeration, then you're safe because your limits all have the same structure. Yeah, but that's a good point to point out. Okay, so now I'm going to get into some people's favorite subject, big Ramsey degrees. Yeah. All right, what are these things? These are things which, okay, so you want to have a structural analog of the finite dimensional Ramsey theorem, right? But since I believe all of us are believers in AC, or at least countable choice, right? We all like omega, right? And there's no philosophical debates there for us. Right, you can always enumerate the universe of K, right? And once you enumerate the universe of K in order type omega, that itself starts introducing these obstructions to getting one color for all copies of the same. And it seems to me, in my opinion so far, that this is really the essential difference. Like the rest of it comes from the structural things that get encoded because you have this order type omega on your universe, but there's nothing besides that that's giving us the big Ramsey degree so far. Okay. I remain to be corrected by more examples later. So finite dimensional structural Ramsey theory is looking for analogs of the regular old infinite Ramsey theorem for structures. So we're going to say K has finite big Ramsey degrees. If for every A in K, there is a number such that whenever you color your copies of A inside of K, you can find another copy of K such that you can get down to T colors. Okay, so color your copies of A inside of K, you can find an isomorphic substructure K, where all the you colored them into R colors, you can get down to T colors. The least such T is called the big Ramsey degree if it exists, right? You said the big Ramsey degree of A in the Freycinet class or the Freycinet limit, both terms are used. Okay, so big is because we are coloring copies of A in an infinite structure, whereas small has to do with finding bounds when you didn't actually get Ramsey property for finite Freycinet classes, but you got some bound, right? So big is for infinite, small is for finite. Okay. So let me just say this, right? If you could get T equals 1 for every K, that would be an exact analog of Ramsey's theorem, but usually you cannot if the automorphism, if you have more than one automorphism of K, there will exist some finite substructures which either don't have big Ramsey degree at all or have a big Ramsey degree greater than 1. Okay, so for all intents and purposes, big Ramsey degrees exist and are usually greater than 1. The times when they are 1 are usually vertex colorings, right? So vertexes, usually if you partition your universe into 2 subsets, right? If you're indivisible, you're going to have a copy in one of these, and so you get vertex colorings with big Ramsey degree 1, but usually for pairs, it's going to go up. Okay, so that brings us to something called, there's been a lot of different terminology in the last couple of years, and we're trying to center in on one. So I'm going to use diagonal diaries. Laflamme, Sauer, and Vuksanovich used similarity types. I used something called strong similarity types some years ago, and we're going to hone in on diagonal diaries. So these record the structural properties, structural meaning more than just the Freycinet structure. Structural properties in an expanded language which is really exactly the same thing as thinking of coding trees. Right, the language is what you have to add to be able to encapsulate the structures you get in coding trees with the structures themselves. Responsible for the big Ramsey degrees. Okay. So I gave some of these in my talk back in January in nice slide form. And now I'm going to draw them slower and hopefully have repetition makes people learn, right? Usually. So I'm going to go through some of those examples, not all of them, but talk about what do I really mean here in practice, right? Okay, so let's look at the rationals, right? The rationals upper bounds for big Ramsey degrees were found by Labor using Millikan's tree Ramsey theorem. And then Devlin completely characterized them in 1979. And this is sort of a retrospective. Okay, that word sounds weird right now. It's a retro perspective using coding trees instead of to the less than omega, because in essence, that's what Devlin was doing. He just didn't really phrase it that way, right? But that's the end game, and that's what we get. So example 1, in terms of coding trees. So we have a bijection. Let's call it B, right? We think of the domain or the universe of Q as being the natural numbers, right? So they're enumerated in order type omega, and maybe Q0, your first one is here. So we're going to make a coding node that keeps track of that. And then maybe Q1 was here. Well, if all you have so far is your first rational, you can be left or right of it, right? So here's your tree of possibilities starting to grow. Can you go right or left, right? Now, if Q1's here, we're going to denote that by a coding node C1. Now you could be right or left of Q1, so that's going to branch. If you're left of Q0, you're already in left of Q1, so you only have one possible way to extend that, right? And then we can just keep building. Okay, and so forth, right? And so you get a dense linear order juxtaposed with order type omega of the indices, right?
The bijection is already an expansion of the length, right?
Yeah.
You could view it as an ordering of the type.
And then there's also the expansion of the language in terms of the tree, right? Left, right, splitting node, height. So, all right. So what are the big Ramsey degrees in terms of this tree structure? They're exactly the anti-chains which code a subset of the rationals, right? So we can make, so big Ramsey degrees here. Given or recorded by anti-chains of coding nodes. And the recording or the record of how these appear in what order is what we're calling the diagonal diary. So if if you have this anti-chain, you're going to have one color, you're going to record split node, right, left. You're going to record terminal node, path, terminal node, right? That's your diary. So any two pairs of nodes which have the same diary are going to have the same color. Let me rephrase that. If you start out, if you start out with a coloring of all pairs of rationals, right, into say 10 colors, right, you can always find a subset of the rationals, which is again a dense linear order, where all of the ones which have this diary have the same color, and then all of the ones which had this diary have the same color. Okay. So if we want to make an infinite dimensional Ramsey theorem on the rationals, we know that how the tree starts to code the rationals is going to affect what color the first pair of nodes can have. And we know we can't get down to one color if we're allowing more than these sorts of types, right? So Right. Let me. I'm going a lot slower than I have 15 pages of notes and I'm on number 4. So I'm going to start maybe not doing so many details and getting on towards the theorems. But let me set this up as an example to hold on to. Okay, so a diagonal diary or diagonal anti-chain where the rationals looks like this. So, okay. We want to make the coding nodes, the nodes which are representing the actual subset of our rationals, to be terminal. So this is some Q sub n1, n0. And then we can either go to the right or left of it. I'm reconstructing that figure, but in an anti-chain. And let's see, the next one wants to go to the right. So we're going to split coding node QN1, left, right, nothing to do there. And then we can split. These do nothing. Next coding node QN2. Okay. So I like to think of things in terms of structures. Andy likes to think of things in terms of embeddings. It's all the same thing, really. You may think of the collection of substructures of this tree structure, which are isomorphic in terms of left, right, splitting, terminal, passing, right? That's a diagonal diary. And what we do for the infinite dimensional Ramsey theorem for the rationals is that fix any diagonal diary. I don't care what it looks like at the beginning, but just fix one. Take all of the set of all of your embeddings of that into itself. That is a subspace of the bare space. This is where it's possible to get infinite dimensional Ramsey theory. Right? And if you don't restrict that much, you are sunk. You cannot get infinite dimensional Ramsey theory. So backdoor. Anyway, we have infinite dimensional Ramsey theory. For this with Q. In fact, we get an Ellentuck theorem because for these things, so what I did was, you won't need forcing, but what I did in one of my papers was to do a large collection of results, which all have a similar flavor to them, which I'll get to in a second. And for the Q-like structures, so Q, Q sub n, Q sub Q, those sorts of things, the property about them is that, I mean, the key property that gets you A32 axiom is that there's no decision to be made except at the coding node. Or in Q sub Q, it's a little more involved than that, but you can make it essentially like that so that the amalgamation axiom still holds. And then A4 I can get by forcing, probably other ways. And we get an Ellentuck theorem actually for this. So, okay. All right, so that brought me to this. All right, so first collection of results I wanted to talk about today is these SDAP results, which are very similar to that, but apply to more types of structures. Okay, so this is the point of this is the property which guarantees that diagonal diaries are simple. Meaning that they look like the diagonal anti-chains used by Laflamme-Sauer Buksanovich. Okay, which is very similar to this, except you need some passing numbers to encode edge, non-edge, relation, not relation, etc. Okay, so this is a property. This is in a paper. It was in one paper, and then the referee said to break it into two. So now it's in two papers with Coulson and Patel. This is defined in number 1. So for those of you who are interested in this amalgamation property, I'm going to go through it. And I'm actually not going to do SDAP plus, I'm going to do SFAP. So SDAP plus for paper. But right now I'm just going to do substructure. So substructure, free amalgamation property. So SFAP. All right, what it's saying is essentially free amalgamation, not triangle free. Right, this is the idea, right? So when you, aside, building on something I have not talked about yet, when you're trying to prove big Ramsey degrees for, say, triangle free graph, right, the previous methods didn't work, and so I had to develop some forcing for them on these coding trees. And the point is that the fact that you had forbidden substructures meant that you had to be super careful how you go about proving the pigeonhole property, right? These are basically saying you don't have to be careful how you're building the pigeonhole property because they all look essentially like unrestricted structures, right? So one way of getting at that, so let's say we have K has SFAP. If, well, it has free amalgamation. And now, given some structures in K of the following, with the following properties, such that C extends A by 2 vertices. Let's call them V and W. B, A is the substructure of B. And sigma and tau are 1 types over B, which when restricted to A look like B and W. Okay. So sigma restricted to A is the 1 type of V over A, and tau restricted to A is the 1 type of W over A. And just keep going here. C, B is a substructure of D, which extends B by 1 vertex, call it V prime, so that the 1 type of V prime over B is exactly sigma, then there will be a member of your class extending D by one vertex. We'll call W prime, so that the one type of W prime over B is exactly tau. And the point is that when you restrict E to A union these new two vertices, you get something exactly isomorphic to C. Okay, so pictorially, let's say we have a structure. Here's A. Let's say it's a graph like this. And then we have some C, which is extending it by 2 points. Let's say V and W. Let's say those have an edge between them, and W is connecting to A2 and A0, and V is connecting to A1. Okay, so this whole thing here is now C, right? And let's suppose you have A embedded into some other structure B, and you want to be able to build a copy of C on top of B, which respects any one types over B that you can possibly throw at it, subject to them looking like sigma, like B and W over A, right? And you can do that. So we have A inside of some bigger B. Now B could be all over the place. Right? And you say, okay, I want to say, I need to extend, that was an unfortunate use of that color there. Now I can't make C that color. So we want something that's going to extend here and here. That's going to look like W. And we want something to look like V. That's going to extend here. Okay, that's supposed to be our W prime. This is supposed to be our V. No matter what else we decide to stick in its one type over B, we can do this, right? So particular radograph has this property. Rationals has it if you allow yourself to finagle a little bit by sticking A inside of a bigger A prime. Triangle free doesn't have this. Posets don't have this, right? So this is like an obstruction to having size 3 sets or more. But something funny happens is that if you look at higher arities, so like the 3 regular hypergraph omitting pyramids, tetrahedron, it does have this property. So that's a little funny thing. But anyway, there, so things which satisfy this property or its strong amalgamation version are the rationals, the Q sub n's, Q sub q's, etc. Everything in Laflamme-Sarah-Vuksanovich's paper, plus if you add a rational linear order to those, it still has this property. And then some of the higher rarities where if you have a free amalgamation class which forbids substructures which are 3 irreducible, which means that every 3 vertices are in some relation, it still has this property. There's a little bit of a weird anomaly. Yeah.
There's probably an edge.
Well, eventually, yes. So eventually, and then you stick this whole darn thing, and so you decide what you're going to take to be V prime. Then, given all this stuff, and given what you've predetermined about W prime to do, there exists a W prime, so that it will have an edge. Yes.
And then also, if I understand, It's these purple edges could be responsible for making a triangle.
That's right.
Okay.
Yeah, it's what could go wrong between what you want these to do over A to get a copy of C versus what you have pre-required them to do over B. Yeah. Okay, so right, so onwards towards the infinite dimensional Ramsey theorem, and then I'll get on to the work with Andy the last half hour. Okay, so in what's now part one, we have a theorem that says that for finite relational languages, of any arity, well, finite arity, this property implies indivisibility. This was a little bit of a surprise. This was a little bit of a surprise because, right, originally I wanted to get big Ramsey degrees for these too, but there's you can go through the forcing and get the pigeonhole, everything's fine, but then the reverse induction breaks down when you have arity 3 or more, right? So you need these, like Hans has been using 2 trees and stuff like that to get around that. But you do still get indivisibility. So vertex partitions, you get a copy of K in one color. Okay, and then in the second one, we do big Ramsey degrees. So for unary and binary relations, and then this implies finite big Ramsey degrees which are characterized exactly by simple diagonal diaries. Right. So simple means very similar to Laflamme-Sauer-Vuksanovich, means looks sort of like that, like the rationals did, except that now you need to encode your relations as you pass by your terminal nodes, right? But other than that, so it's just given by, you record where's your splitting nodes, you record what's right, left, you record what relations have been encoded, you record where's your terminal nodes, that's it. That's your big Ramsey degree description for these. Okay. And then, so building on that, yes. Yeah. Yeah. Sort of, yeah. So SFAP implies SDAP plus. It's a bit stronger, yeah. And then the SDAP is basically that thing, except before you choose B and D, you're allowed to grow A and C to make sure you don't get obstructions. You like take care of what could go wrong first, and then you go. But the characterization is exactly the same in terms of these simple diagonal diaries. Yeah. Okay. Right, and then, oh yes, So I did want to point out, so something also that was very fun about this proof is that we just got these exact big Ramsey degrees directly. We didn't have to go through the usual methods of envelopes or whatever. You just prove them. The upper bounds are exactly them. You do a little argument to show that they're the lower bounds, and that's it. So now starting with those, now the breakdown starts to happen between the free and the non-free amalgamation. So if you fix, let me put it this way, fix a strong diagonal diary delta actually is strong. Then for each okay. So we get a Galvin-Perkry analog for this space when K has SDAP plus, and for we get an Ellentuck analog for these spaces when K has K is Q-like. Q-like meaning Q or Q sub n or Q sub Q or those sorts of things. The things that, I mean, like the property that gets the A32 to work, I think I said this already, is that essentially when you make your diagonal diary at your coding node level, there's really no choice for anything going by it except the ones that just came off prior to that point. Yeah.
Finally, I was waiting for this last statement. Because you see, you cannot state the statement without telling you what's the final approximation.
Yeah, okay.
And so I was waiting for this whole time.
Ah, okay. All right. Okay. So finite, okay, so.
Doesn't exist without S.
Yeah. Yeah. Yeah.
The Galvin can be just topology.
Yeah.
It has nothing to do with approximations.
Yeah. So, and that's a very good point. So, there are a couple of things at play here, right? These, the way I have set them up, the finite approximations are by initial segments in the coding trees.
Just they grow up one by one.
They grow up one by one. So, so splitting nodes matter, coding nodes matter, everything matters, because you can't get around that except in the case what I called good diagonal coding trees in that paper is the case where at each level of a coding node, you have exactly one extension per one type over the initial structure built so far, then it's equivalent to just looking at the structure. So then you can go by first vertex, second vertex, third vertex on those. But if you don't have it quite so fine-tuned, you can't go quite back to the structures. Then you're really just working with the diagonal diaries.
The initial segments of these diagonal diaries are like level trees.
Yes. Yeah.
Yeah. Preserving.
Yeah. Just, I mean, just like Millikan, except that it's skewed.
Anyway, whatever it is, you see, be careful with the, when you started your talk, you were telling us a finite dimensional and then there's a S as the initial part, define an entity in symmetric topology.
Yeah.
But you see, this S was the part of the structure T. There's no additional structure there. And here you are putting it.
Yes. It's
what I'm saying, if you are putting this means, etc.,
yes.
These are really not Unwell. We have to- it's a-
It is in the expanded language. It is in the expanded language of the
While
of the
for-
big
while
Ramsey
the first
structures.
theorem that we don't need to mention that.
Yeah. Okay. All right, so in the last 24 minutes, talk about joint work with Andy. Yeah, I mean, that's all made clear in the paper. It's not like I've not done that. I'm just in a talk, it's sort of a lot to put on the board. So in joint work with Andy, we're looking at binary free amalgamation classes. So we've got L is a finite relational language. With relations of arity at most 2. And what is free amalgamation? It is really the same thing as looking at the L structures, which forbid some collection of finite irreducible substructures. Okay, so for F is a finite collection of finite irreducible structures. Okay, so think about triangles, think about 4 cliques, think about you could have 2 binary relations, you could leave out 5 cliques in one and 10 cliques in another. You could have, you know, say red and green edges, and you could leave out triangles that have like red, red, green, right? That's that sort of thing. K-partite graphs, because we're allowing for unaries in this setup. And so the upper bounds for this huge thing were done by Andy, which we're building on my prior work for the K-clique free graphs. And then the lower bounds were done by in this 7 people group of Balko, Hodansky, myself, Hubitschka, Konieczny, Vena, and Zucker. And then building on the lower bound structure, we set up the infinite dimensional theory. Okay, so theorem 1 with Andy. Okay, so we're going to let gamma and theta be any diagonal diaries. Encoding. Okay, right. So diagonal diaries are essentially diagonal anti-chains, which have some more pieces to them because now they are coding how fast did your forbidden, pieces of your forbidden substructure appear, which affects which structures are able to extend the finite structure that you've built so far, right? And so they look like what we've looked at already, except there's that extra bit now. And then there's another bit at coding node levels that try to reduce the paths that you can have above there. Okay, but anyway, basically you can think of these as diagonal antichains, which are encoding your structure K. Okay, and any two embed into each other because you know, K has all these different copies of itself. And then okay. I will tell you what this means in a second. So for any finite Suslin measurable, coloring of the embeddings of theta into gamma, there's going to exist some embedding of gamma into gamma such that when you interpolate everything through H, you have the same color. So again, what's the topology? So we have these diagonal diaries, which you may think of as the big Ramsey structures, which means we've expanded our language a little bit to include what the tree structure is and so forth. But again, the initial segments level by level in the trees are what are the finite heads of your Ellentuck topology here. Here we're not even using that yet.
Here you are still on the
Here we're,
arrow
yeah,
baseline.
yeah. Here we're still, yeah. Here we're still using just the regular metric topology.
Is this measurable as well?
I mean, it's closed under the Suslin operation.
So you can
The-
actually go
Yeah, the smallest sigma algebra is closed under that.
just behind this,
Mhm. Right. And let's see, so this is theorem 0 because it precurses that one. Okay. So in chapter 4 of Stavo's book, we're just leaving off the finite approximation notation. And I should tell you what these things are. Let me, all right, let me jump ahead actually before I get there. We're going to fix strong diagonal diary. Delta. And a diagonal diary. Theta. And we're going to let R be the set of strong embeddings of theta into delta, and S is a set of embeddings which have an extra nice property, delta into delta. Levels, delta, And identity below mu. And this is probably not going to make sense, but I'll try to talk it through. Okay. So we're playing with two types of diaries, right? These strong diagonal diaries are very, very stratified. So if you take just your general coding tree for, say, a k-click-free graph, and you make a diagonal anti-chain, which is going to encode it. One way, and the sort of simplest way and the strongest way to do that is by splitting levels at different heights to get as many nodes as you need to have passing numbers that you need. Then you start to fill in with all of the possible obstructions, we call these age changes. And then you have a third type, which is these controlled coding nodes, and those come in. And then you have the actual coding node and the passing number. So there's like 4 strata between each 2 coding nodes in these strong diagonal diaries. And we do them in this particular order. And so a strong embedding is going to take one of these to one of these in these, a level with splitting node is going to go to a level with splitting node. A level with age change is going to go the same toward of age change. A level with, witnessing a controlled coding node is going to go to. So those are the strong ones. The diagonal diaries are just anything that encodes K that's diagonal anti-chain. Okay. So we have these 2 types, and this is what we are interested in, but we're going to interpolate through here. And then, the finitizations are just taking these embeddings, restricting to the first M levels of theta or delta. And then we have our lesser equal relation and our lesser equal R relation. We have sigma's lesser equal to phi if and only if sigma is in G composed with S, and lesser equal R is on R cross S. So we have eta lesser equal R phi if and only if eta is in phi composed with R. Okay. So it's like we're going from theta to delta. This is our S, this is our R. Okay. I'm not going to write that. Okay. And so we have our theorem. Just in general, if you have the Ramsey space set up in Stavo's book, and there exists something we're calling an A32 ideal. Then this quadruple is a Ramsey space. All right, so from this theorem plus our setup, we end up with the theorem one, wherever I put that there. And if you restrict to, if you require the theta to be a strong diagonal diary, then using this finite approximation setup via these
And we should
very
mention
strong
what-
trees.
what Now, on this space mean.
Yeah.
The conclusion of Ellen's theorem is true. But to get inside the set, you don't need to increase that.
Yeah.
estimation.
Right. Yeah. Right.
On the membrane, but is theorem two gonna be that this RNS over here is a Ramsey space?
What?
Are this RNS over here going to form a Ramsey space?
Yes, yes. I think I just erased the wrong one. Yeah. Right. And then if you have strong diagonal diaries on both instances. Right. When R equals S, we get analog. Okay. So, I mean, I could give definitions of all of these, basic open sets and all of that, but I think you probably all own Stavo's book anyway, so
Well, I
you
mean,
don't know them by
there-
heart, you
there's
could look them
there
up.
Topology.
Hmm?
They're gonna be topology.
We get this,
It's a topological on this space.
yeah, it's a topological Ramsey space. With respect to these particular strong diaries and their initial,
And also
segments.
This is, you are going, this should be stronger than these other results.
yes, that's true. Yeah, that's really a corollary in a sense, yeah. So I could stop there. Let me just say a little bit about the proofs, because I haven't given any proofs today. I was trying to get some structural ideas across, which hopefully I did. So the proofs, this one, no, where'd it go? Anyway, the proof that says that A32 ideals are sufficient to replace A32 is done basically by just going through the book with the combinatorial forcing and just replacing all the uses of A32 with the A32 ideal. It's really nothing more than that. And then the pigeonhole principle is still done by forcing with these diagonal diaries. But we made their setup nicer than before, so it's a little bit cleaner than the other proofs of forcing to get pigeonhole. Okay. So I think I'll stop there.